There it goes!
Yay! I made a 2D version of a greedy cup siphon recently, and Matt Parker suggested that I might be able to build a water computer by chaining together a number of these siphons. For example, maybe I could use these siphons to add numbers together. Computers add numbers by chaining together a series of logic gates. For example, these logic gates add two-digit binary numbers together. I'll get into the details of that diagram later, but what are the logic gates made out of? Well, in a computer, they're made out of transistors, but they don't have to be. If you're familiar with Matt Parker's channel, you'll know that logic gates can be made out of dominoes, for example. But what about using the flow of water instead? This was my first attempt. If both inputs are turned on, they collide in the middle, filling up this central bucket, and water flows out of the middle hole there. If only one input is turned on, there's no collision, and water flows into one of the two side buckets. In other words, water only pours out of this output if both inputs are turned on. In a computer, you call that an AND gate, a logic gate where the output only turns on when both inputs are on. If I combine these two outer holes into a single tube like this, then water only flows out of this tube if one or the other of the inputs are turned on, but not both. In a computer, that's called an exclusive OR gate. So this should work as an AND gate or an OR gate, or both at the same time. Actually, this arrangement fails immediately because water is too sticky. It sticks to these outer faces and you can't get a jet strong enough to pass across the gap. But if you can separate the water from the glass, you can get it to work.
What I did like about that one is you can very easily see why it works.
Yeah.
And that's why I love these ridiculous physical computers, because there's no magic to computing.
One slight issue is flow rate. So for example, if the flow in is slower than the flow out, this is going to build up and then it's going to spill over. In the end, this mechanism had too many issues. Also, I really wanted to use the greedy cup siphon mechanism, which this doesn't have. Actually, the reason Matt Parker thought of water computers while watching my video was because of a mistake that I made. I put the siphon in the middle of the container that actually split the container into two independent areas.
I did enjoy your video, watching you having to pour both very carefully to synchronize. It had that sense of an and.
There really is an andness to it, isn't there? The problem is you have to really worry about timing. Both those bits from each side have to come in at the same time. They have to meet at the same time at the top there. Actually, you can get a much more reliable AND gate from this thing. What you do is you define a 1 as a certain volume of water that gets just above halfway on here. So if you put two 1s in, the volume of water gets all the way to the top, the greedy cup siphon is activated, and your AND response comes out there. An exclusive OR is a little bit trickier.
I sent you a sketch where I had a dual height greedy cup siphon with one on each side but different heights, which I thought would work, but I wasn't sure if it would be reliable.
So in the end, the solution was to drill a small hole here. It's a slow leak. And what that means is if you put a 1 in there and only a 1, you're not going to get a greedy cup siphon, but you are eventually going to get it to all come out of that slow leak. If you put two 1s in for your input, then the siphon is activated and the chamber empties. It doesn't empty instantaneously, so there will be a small amount of leak through the exclusive OR channel. So when you look at the chamber that's catching the exclusive OR output, if there's just a little bit at the bottom, you read that as a 0, but if the chamber is full up to here, then you read it as a 1. One thing that's nice is that this single device houses two gates. You've got two inputs and two outputs. One output gives you the exclusive OR, the other output gives you the AND.
Conceptually, we had to switch from thinking about something you would turn on and it would just keep flowing and settle into some kind of state, to now you've got packets of water representing bits.
Why don't I show you? I can't change cameras, so why don't I do a WhatsApp video call with you? I know. Sure. Oh, you've just... Why did you reject my call? That's very rude. Are you screening my calls?
Hey! All right.
Hey! So I'm going to
mute you here.
There it is.
Oh my goodness! I have no sense of the scale of what I'm... Well, I know the scale of the achievement.
It's pretty cool, isn't it? But what on earth is it doing? Well, it's implementing this logic gate diagram that I showed you before. Actually, if I turn it on its side, you can start to see they have a similar shape. But what exactly is this logic gate diagram doing? Well, at this point, it's helpful to switch up the language that we use. Instead of talking about inputs and outputs being turned on or turned off, let's talk about ones and zeros. So for example, in the case of an AND gate, you would say if both the inputs are a 1, then the output is a 1. Thinking about the logic gates in that way, we'll be able to show that this particular arrangement is actually going through a process of long addition of binary numbers. You'll note from doing long addition at school that if you add 2 digits together and it goes above 10, then you carry the 1. So for example here, 9 plus 4 is 13, you put the 3 down there and you put the 1 up there into the next column. The same thing happens with long addition of binary numbers. If there's a 1 and a 0 in this column, then you put a 1 down here. But if there's a 1 and a 1, well, 1 plus 1 is 2, and 2 in binary is written 1, 0. So you put the 0 down here and you carry the 1. You might already be noticing some logic gates hidden in these operations. For example, the number that you put down here, if you think about that as the output, what we have is an exclusive OR operation. You only put a 1 here in the output if one or the other of the inputs is a 1. If they're both 1, then you actually put a 0. What about the carry? Well, the carry is related to those two inputs like an AND gate. In other words, you only carry a 1 if both of the inputs are a 1. So let's put that together in a diagram. This is called a half adder. Moving to the next column in this long addition, there are actually 3 inputs. So the logic diagram is a little more complicated. Here it is. I'm not going to explain it all, but feel free to pause the video if you want to ponder it for yourself. But this is called a full adder. And if you want to add, say, 2 4-digit binary numbers together, you just chain 3 full adders together like this with a half adder at the start because the first column doesn't have a carry coming in. Because our devices are an AND gate and an OR gate in one, we can simplify this logic diagram to look like this. Some aspects of this water computer aren't completely obvious, like this bit here, for example, it's a splitter. The reason you need a splitter is because, well, if this siphon activates, it's because you've put 2 1s in. You've got a volume of water that represents actually a 2. So you have a 2 coming out of here, but I only want a 1 to go in here, so I need to split it in half. A 1 goes this way and another 1 goes this way. This is just a drain. I originally had one continuous tube for the drain, but that was acting like a siphon and preventing any water going into this one. That's why you've got this funnel here. It just breaks that siphon effect. This bundling is also a bit confusing. Honestly, that's just for tube management. If you look closely, it is just 2 separate inputs, this one and this one. Really, I should have an XOR tube coming out of here into a readout bucket like this one, but it's a lot easier just to not bother drilling a hole in here, and then this doubles up as the readout bucket. You might be thinking, well, hold on, this has got 3 inputs. How can that work? And actually these 2 inputs should really go through an exclusive OR before going into here, but it doesn't really matter because you would never actually get both of those on at the same time if you consider the logic prior to these 2 tubes. So it's fine to just have them both go straight in. Do you want to give me 2 numbers to add?
I kind of want to see 11 plus 5. The reason I think that'll be interesting is you're going to have different types of cascading rollovers.
So let's put a 1 in there. A 1 is 10 milliliters, by the way, in case you're wondering.
Oh, that's good to know. I've always wondered what the volume of a 1 is.
So these are the 2 numbers we're adding, 11 and 5, written in binary. You take the 2 digits from the 1s column, put them in these syringes. The 2 digits from the 2s column, put them in these syringes. The 2 digits from the 4s column, put them in these syringes. And the 2 digits from the 8s column, and put them in these syringes. We're then going to watch these 5 readout buckets. You've got the 1s bucket, the 2s bucket, the 4s bucket, the 8s bucket, and the 16s bucket. 11 plus 5 is 16, so we want a 1 in that final bucket and nowhere else. Hey,
there it goes.
There you go, it worked. So now, and then that one should roll over.
And then the next one?
Oh, come on. Ah, balls. Part of it is getting the right amount in the syringe. You don't want too much so that there's too much dribble left over and so on.
Maybe a 1 is 11 milliliters.
I also think we've got a bit of an issue here where some of the water's dribbling down the backboard.
You've got a memory leak, Steve. I've never been so proud of such an easy joke. Could be a security issue if I'm honest.
Yeah, I think someone's using this to mine Bitcoin and it's slowing everything down.
What if we generate 2 random numbers and we'll give the computer a good clean out and we'll add the 2 random numbers so we have no way to influence this, and if that works, we declare it a raging success.
Okay, that sounds good.
Got it. So 4 plus 9. And that's pretty close to the 9 plus 5 that we were thinking would be a good idea. That's going to be pretty boring because it's all just going to plonk through. Tell you what.
Or do you want to?
Oh, I just had a closer look, Steve. It was a 5. Huh.
Oh, right.
Oh, mate, I'm sorry.
The reset is like, I lift this up, I go like that, and then I go like that.
The Etch-a-Sketch approach to resetting. Underused in modern computing. Although the undo on an iPhone is a shake. So the Domino's reset was a day if you have a team of like tens of people. I got 2 3-digit numbers working on the Domino computer. If you get this to work, this would be a substantial increase in computing power.
All right, here we go.
Okay, bam. We've had our and. Because that still could have gone wrong. Like, I know we're saying it's a trivial calculation, but that split had to work. And now we just need 2 slow leaks.
Which is what we've got. It's 0, 1, 1, 1, 0, which is 8 plus 4 plus 2, which is 14. What were we adding together again?
9 plus 5.
Is 14, yay!
In my experience, the more facetious of the commenters on this video will point out that you just went to a lot of effort to show that 9 plus 5 equals 8 plus 4 plus 2.
Of course, that's not really a fair comment because you only do the 8 plus 4 plus 2 bit at the end when you're converting back to decimal in your head. If you stay in binary like a computer, then we've actually done something really useful. We've shown that 0101 plus 1001 equals 01110. You know, maybe I could build something that converts it to a decimal readout.
Your water computer, my Domino computer, there's discrete states that it ends up in. So it probably can't say analog. But there are actual analog computers. So famously, there's a guy called Bill Phillips who was an economist and worked on dams and realized the equations for water flow matched the equations that are used to model the economy. And they built a actual analog water computer to model the economy, like with taps for like government spending and interest rates. This is kind of before you could just numerical solution your way out of the problem. In other news, Steve, I've just looked up, you are on 877,000 subscribers. I am on also 800 and something. We're going to keep collabing until we get to 1 million.
You challenged me to the water computer. I want to see a video on the game Dobble.
That is one of the most requested video topics.
Is it?
And there's no like accessible videos on it.
That's going to be a really interesting video, so make sure you subscribe to Matt in advance, link in the card and the description. He's approaching 1 million subscribers, so let's get him there as quick as we can. I'm also approaching 1 million subscribers, so if you're not subscribed and you've watched a few of my videos, I'd love you to consider whether I've earned your subscription. Should we do one more calculation? Maybe slightly higher numbers or something, so we get down to that final bucket?
Yeah. What about like 7 plus 15?
Yeah. Here we go.
Okay. Units are in. Units are overflowing. We got an and.
Yeah.
Oh, yep. 2's have overflowed. We've got an and.
There it goes.
Okay, the waste seems to be working. Just dump that one.
There it goes.
Now we just need one more and. Come on.
Come on.
There's enough. Surely there's enough coming in. There it goes!
Yay!
You've done it! 7 plus 15 equals 22.
For completeness, here's that original calculation, 11 plus 5, actually working instead of failing. And just for fun, here's 15 plus 15. In other words, all the ones. I didn't go into detail about how binary numbers work in this video. If you want to brush up on that, I can heartily recommend the sponsor of this video, Brilliant. The best way to learn something is by doing it for yourself. Like if you want a really long-lasting intuition about something, That's the way to go about it. Brilliant took that principle and turned it into a website and an app. It's a fine-tuned learning experience. They throw you in with these problems that you have to solve, and it's all interactive stuff. When I say it's fine-tuned, I mean they've given a lot of thought to things like the difficulty progression, so you never feel like you're getting stuck. If you ever do get stuck, they have these clever mechanisms for getting you unstuck without feeling disheartened. The result is something that's incredibly satisfying. They've got courses on broad topics like science, maths, engineering, or you can take a deep dive into very specific things like cryptocurrency or quantum computing. And of course, they have courses on binary numbers. Actually, I used Brilliant to get unstuck in my orbital resonance video. It really helped me to understand the papers I was reading. But to be honest, I mostly use it for fun. You know, a lot of people might read a book at bedtime, not me. You can try out brilliant.org for free, no commitment, using my special URL. It's brilliant.org/Steve Mould. The link is also in the description. So why not join me and 8 million other lifetime learners by going to brilliant.org today. I hope you enjoyed this video. If you did, don't forget to hit subscribe, and I'll see you next time.